We're going to talk about observational studies and experiments, the difference between the two. We're also going to look at this idea of confounding and what a completely randomized design is and what on earth is blocking. So first of all, an observational study is where we just simply look at what's going on. We don't try to influence or impose any kind of treatment. We're simply there as recorders of fact. But an experiment, on the other hand, is going to deliberately impose some kind of treatment. We're going to tell some people to do something and some people not to do something. So in an observational study, we're describing, we're comparing, we're examining relationships. It's important. We're getting something out of it. However, when we experiment, we get more. In fact, we get the thing that we want most of all, which is cause and effect. And we have said that correlation does not imply causation. Well, experiments, if done well, do imply causation. This idea of confounding is when you do an experiment, you get a lot of background noise. You get other variables sometimes in there with the variable you're trying to study. And so what we want to do is make sure that we're not confusing one variable's effect for another. And the best way to describe this is by looking at an example. So if we're asked to find this possible confounding, we need to give some sort of a plausible story about why it would connect to the variable that we're looking at and how it affects that response variable. And common sense is all that's really required here. So for example, if the ABC News says, well, teenagers who eat with their families are at least five times a week are more likely to get better grades in school. So what variable may be confounded with that? So what we're saying is, does eating with your family cause you to get better grades in school? And the answer is sadly no. It's more complicated than that. So for example, we know that families that eat together 5 times a week tend to be economically stable. And in homes where there's economic stability, students do tend to get better grades in school. So that might be explaining what's going on. Also, there may be a higher educational level of the parents, and that certainly helps their children. So let's just talk language here. Okay, when we're imposing something, where we're saying we would like you to do something, or we're going to do something to you, that's called a treatment. We're going to have different levels of treatment, perhaps. And what we do those treatments on are called the experimental units. Now, we want to dignify humans, and so we call them subjects. But if we're talking about objects like steel girders, M&Ms, different kinds of cars, those are experimental units. And humans are always called the subjects of the experiment. So here's a great example of how you could design an experiment. So let's say we're going to expose people to commercials. And we want to know, should we expose them many times to the same commercial? And does the length of the commercial matter? And so you would take your volunteers, because usually they are paid volunteers, or sometimes just purely, not doing it for money. Sometimes they're just interested, but most of the time they have to be paid. We bring them in, we divide them into 6 groups, and then each one of those 6 groups that then forms becomes a treatment. And then the number of times or the amount of seconds are called the levels of those factors. So the factors here are the different variables that you're studying. So one thing you could do poorly when you create an experiment is something like this. So let's say that a school is going to offer an SAT review course, but it's going to be online. So the group who takes this online course, say that they get an average of 45 points better in their math scores. So there's obviously like a pre-test and a post-test. So can we conclude that the online course is effective? Well, you say, well, look, they went up by 45 points. How couldn't it have been effective? Well, if you think about it, so here's the design, right? We're taking students, we're sending them through an online course, and voila, out the backside, they've increased in their math scores. But question you've got to think to yourself is there any other way that the increase in math scores could have happened? And so here's one plausible idea is that, well, these students, let's say they were taking an advanced math class. Let's say they were taking pre-calculus or, algebra 2 or integrated 3 or whatever. Well, maybe that's why they improved their learning in their math, not because of this review course that we sent them through. This is what we call confounding. And it's preventing us from concluding that the online course is effective. How do you get around that? Well, glad you asked. So what we have to do then is we have to not allow the students to select which method of learning they're going to get. Don't let them choose the treatment. If you're going to have some students take the review course, you assign them randomly. The other students, maybe they don't get to do anything. Maybe they don't get a review course at all. But the key is to eliminate bias, you have to randomize. So in this random assignment, as we've talked about before, one of the ways to do it is called the hat method. That means assign everyone a number, put those numbers in a hat, and select the numbers out of the hat. You can do this in computerized ways. You can do it on random.org. You can do it on a graphing calculator. You can also use a random number table. And the idea is that if there is a bias or if there isn't something going on, at least randomizing spreads that effect out evenly. Now, the idea of control, you gotta forget what you think you know about the word control for a second. It just means keeping all the other variables that we're not testing the same. That may not be possible completely, but as much as possible. So for example, if you're going to take the SAT test, have the students who took the review course and the students who didn't, let them take the exact same test on the exact same day with the exact same setting. For example, you wouldn't want to give the kids who had the review course, you get a candy bar before you test. And the kids who didn't, we're going to give you a bottle of water or something like that. No, we want all of the situations to be the same so that we can point to the differences and say, oh, the differences must have been because of the treatments. Now, replication can be thought of in two different ways. One way you can think of as replication is you should be able to do an experiment anywhere in the world and get the exact same results. You do it in Australia, you should get the same results you would get in South Africa, as in France, as in New York, or whatever. But in this case, what we're talking about with replication is, did we have enough students or enough experimental units in our experiment? And the reason you want to do that is one person does not make an experiment. So we call these testimonials. I did this and this worked for me, so therefore it should work for everyone, is not scientific thinking. It's anecdotal, it is evidence, but it's not going to establish causation the way that we want it to. So in summary, we want to compare two or more treatments. We want to have random assignment. We don't want to let people choose what happens to them. Or if it's objects, we want to randomly assign them out. We want to try to keep all the other variables in the experiment the same. So think of it as the same experience, except for our treatment. And replication just means let's do it on enough people so that we know that what we're seeing here works in groups. Now, there's no magic number on that, but you'll see a lot of problems in the book talk about, well, they did this to 20 people. And that seems to be anywhere from a dozen to thousands of people may take part in an experiment. Now, here's a very famous experiment that's mentioned in the book. It's called the Doctor's Survey, or the Doctor's Experiment. First of all, they want to know, does beta carotene prevent cancer, and does aspirin prevent heart attacks? And what they did is to keep control, they used 21,996 male physicians. And the idea there was, okay, they're all male and they're all physicians, so they have the same stresses in their life, the same physiology. And if you think about it, physicians are used to doing things in a regimented way, so they're hoping they won't forget to take their pills. So for explanatory variables, did they take aspirin or did they take a placebo? Did they take beta carotene or did they take a placebo? And if you think about it, that makes 4 different treatments. Here's the chart on that. So you want to put a placebo in there because everybody needs to feel like they are taking something that's going to help them. That way they all have the same mental attitude about what they're doing, and that doesn't become a confounding variable. So the odd numbered days, the subjects took the aspirin or the placebo, whichever one they'd been assigned, and on the even numbered days, they took the beta carotene or the placebo. Now, this experiment was cut short. One thing they found out is that beta carotene really didn't do anything at all. But the aspirin did make a difference. In fact, it had a life-saving difference. And so even though the numbers you're seeing here are relatively small compared to the size, right? So 239 of the placebo group, but only 139 of the aspirin group suffered heart attacks. Still, you're talking about 100 people that it perhaps saved the life for. So they stopped the experiment early and they said conclusively, okay, aspirin prevents heart attacks. Now, of course, there were follow-up studies. You have to figure out what's the right dosage. And that's why even today you can go into like a CVS or a Walgreens and they have these baby aspirin that you can take. So just to review, did they follow these principles of design? Yes, they did. Both groups took some kind of treatment, either an active treatment or a placebo. And then there was random assignment into 4 groups. The experiment, it was the same gender, the same occupation with the same schedule of taking pills. And look at the size. There were plenty of people that were included. So we had replication. So you'll see this thrown around every now and then, completely randomized design. It's basically what you want to do when you have experiments. So a little tip on the test, you will be asked to describe the design of an experiment. So you might want to start with a diagram, just kind of figure out how that would work, and then go to a narrative, and then what they would judge you on is anything that you write down. So it's either the table and some notes you jot down, or just go right to a narrative, go right to a paragraph. Who's going to take what when is basically what you have to answer. So what can go wrong? Well, what can go wrong is that, for example, if I know that I'm giving you something that could save your life, I'm going to act differently than if I know that I'm giving you a placebo. It will be written on my face. It might be in the tone of my voice. It might be, somewhere present on my demeanor. So many patients will respond favorably to placebos. We know this, sort of. There's some current evidence that contradicts this a little bit, but still on the AP test, so we're going to go with it, that there is an effect, a positive effect, just by believing that something is going to help you. But if you tell the people that are administering the drug that, hey, this is going to help the patients, that might affect their behavior, and that might be a confounding variable. So what we do instead is we do what's called a double-blind experiment whenever possible, whenever practical. And that means neither the subjects, the ones getting the treatment, nor the ones giving them the treatment should know which is the real treatment and which is the placebo. So if you hear that an experiment was a double-blind, completely randomized experiment, that's usually the best form of experiment. Now, later on in the course, we're going to talk about statistical significance. And basically what it means is that we believe that the result was so rare that it couldn't have happened by chance, that the treatment that was given was the reason why there was a change. And when we have significance like this, it does imply causation. Blocking is a way to put groups together that have something in common. Now, again, this is better explained with an example than theoretically. Okay, so here's their example. So you got to go with this. This was written many years ago, before we had really a lot of smartphones on the market. Now everybody has a smartphone, right? But there used to be dumb phones, Nokia phones that were a lot harder to text on. But anyway, let's suppose that a mobile phone company is testing keyboard designs. And so what they might want to do is test it on a group of volunteers, but the volunteers may have something in common. Some may be used to texting with similar keyboards and some not. So here's the idea. We're going to randomly assign, but do you notice that the blocking is not random? So you might ask someone before they start the survey process, or before they start the experiment process, have you ever used a smartphone before? So years and years ago, imagine that only 4 said yes and 6 said no. So then you test those 2 keyboards, randomly again assigning, but you're keeping the data separate for those who had used smartphones before and those who hadn't. At the very end, you try to compare the results. Now, in this graph, on the top graph, you have not tagged the data at all. It's everyone's data. It's hard to tell what's going on. But in the second graph, what you'll notice is that all of the squares, which are the smartphone users, are pretty well ahead of everyone else. So we should really only compare the circles to the circles and the squares to the squares. And in that way, you can tell that keyboard A was clearly the better keyboard, because for the circles, like the fastest on keyboard B was 25, but that was the slowest for keyboard A. And similarly, the fastest for keyboard B was 40. Well, that was even slower than the slowest for keyboard A, which was around, 43 or 44. So it was useful to make a block. So think of a block as just sorting people out into different groups. So here's the moral of the story. You block what you can't control. You control what you can. You try to make the playing field even. When the playing field is not even, you basically tag the data. You block it out so that you're comparing like things with like things. And you still have to include randomization in there. That's what's going to be your key to control bias. One last tip, don't mix the language of experiments and surveys together. So a big no-no would be this phrase, use a randomized block design to select the sample for the survey. No, randomized block design is only for experiments. It's not for samples. It's not for surveys. And the other no, this experiment suffers from non-response and some subjects dropped out during the study. Non-response is something that refers to when you're trying to give a survey question and people won't or can't respond. That is not what happens at all in an experiment. So you're going to have to try to, in your mind, keep these two ideas separate. Well, that's the end of this lecture. We'll see you next time.